On the morning of April 6, 1945, 355 Japanese aircraft lifted off from airfields across Kyushu. They were not flying a mission. They were flying a funeral, their own. Each pilot had been told the same thing: find a ship, aim for the waterline, and do not return. By sundown, 14 American vessels had been hit. 2 destroyers were gone. The USS Bush and the USS Calhoun, both sunk within hours of each other, both overwhelmed by waves of aircraft that kept coming long after the guns had grown hot. It was the opening act of Operation Kikusui. Floating chrysanthemums. 10 mass kamikaze raids across 10 weeks. The largest organized suicide campaign in the history of warfare. By the time Operation Iceberg ended at Okinawa in late June, 368 Allied ships had been hit. 36 had been sunk. Nearly 5,000 American sailors were dead. More naval casualties than any other campaign in the Pacific War. And yet the number that mattered most was not in any headline. It was buried in a Bureau of Ordnance post-war assessment, completed in the autumn of 1945. Analysts combed through gun camera records, damage reports, and anti-aircraft logs from hundreds of ships. They were looking for one answer: what had actually stopped the kamikazes? The Bardij Satyo, Baitur Sirenai 50 caliber machine guns that lined every deck accounted for a fraction. The 20mm Oerlikon cannons, fitted by the thousands, had a kill rate that disappointed. The 5-inch guns fired proximity-fused shells that could shred a formation. But the kamikazes came in low, fast, and alone. The proximity rounds often detonated too late. One weapon appeared in the data with a consistency that nothing else matched. A gun that fired 40mm shells at 120 rounds per minute. A weapon that could track a diving aircraft and put steel on target at ranges where the pilot still had time to pull out, if he intended to. The Bureau of Ordnance credited it with approximately 32% of all confirmed anti-aircraft kills in the Pacific theater. That weapon was not designed in an American factory. It was not built to a Navy specification. It had not been developed under a Pentagon contract or tested at a naval proving ground. It came from a small industrial city in central Sweden, designed in the early 1930s by a company whose primary business was steel and artillery shells, and the United States Navy had nearly refused to adopt it in 1940. But the real story of the Bofors 40mm is not the gun that stopped the kamikazes. It is the story of how the most important anti-aircraft weapon of the Second World War had to fight 2 wars simultaneously. One against the enemy in the sky, and one against the institutions that almost never let it reach the deck. Every week, we tell the stories behind the weapons, the programs, and the decisions that shaped American military power. Give the video a like and subscribe if you want to keep hearing them. The story begins not in Washington, and not in a Navy shipyard. It begins in Karlskoga, Sweden, in 1928. By the late 1920s, military planners across Europe had begun to recognize a problem that no existing weapon solved cleanly. Aircraft were getting faster. The gap between what a slow traversing artillery piece could track and what a modern biplane could do in a diving attack was widening with every year. Heavy anti-aircraft guns, the 3-inch and 4-inch pieces that had defined the Great War, were designed to engage bombers flying high and straight. They needed time to calculate the firing solution, time to elevate, time to load. Against a fast-moving attacker coming in low, that time did not exist. At the other end of the spectrum, the light machine guns mounted on ships and field positions could traverse quickly enough. But their caliber was too small. A 30 caliber or 50 caliber round could wound an aircraft against a determined pilot willing to absorb damage and press his attack to the last second. Wounding was not enough. The bullet that stopped the engine had to reach the engine. At ranges beyond 500 yards, The small caliber rounds simply lacked the energy to do consistent structural damage. The gap between the heavy gun that could kill but couldn't track and the light gun that could track but couldn't kill was a 40mm hole in the air defense of every major military in the world. Aktiabolaget Bofors was not a weapons company in the modern sense. Founded in 1646 in Karlskoga, a mid-sized industrial city in central Sweden's Värmland region, Bofors had spent most of its existence producing steel, iron, and later commercial explosives. The company moved into ordnance manufacturing in the 19th century, supplying artillery shells and propellants to the Swedish military and to export customers across Europe. By the early 20th century, Bofors had established a reputation for precision metallurgy, the kind of exacting tolerances that artillery performance demanded. In 1928, the Swedish Navy issued a requirement for a new light anti-aircraft gun. The specification called for a weapon capable of engaging fast, low-flying aircraft at ranges up to 3,000 meters, with a rate of fire sufficient to put a continuous stream of projectiles in front of a crossing target. The caliber was set at 40mm, large enough to carry an explosive shell that would damage or destroy an aircraft with a single hit, small enough to be fed automatically without a dedicated loading crew. The Bofors design team, led by engineers Emanuel Jansson and Birger Hallen, began development that same year. Jansson had spent the previous decade working on automatic cannon mechanisms, the feed systems, bolt carriers, and recoil buffers that determined whether a gun could sustain a high rate of fire without jamming or overheating. Hallen's background was in fire control geometry, the mathematics of leading a moving aerial target. Together, they approached the requirement not as an artillery problem, but as a mechanical timing problem. How do you place a shell in the future position of an aircraft that is moving at 200 miles per hour in 3 dimensions? Their answer was a 4-round clip-fed automatic cannon with a cyclic rate of 120 rounds per minute, mounted on a pedestal carriage that allowed 360-degree traverse at a speed fast enough to track a crossing aircraft. The barrel was 60 calibers long, 60 times the bore diameter, or roughly 94 inches, which gave the shell both velocity and stability at range. The complete system, gun plus mount, weighed approximately 1,180 pounds in its naval twin configuration. It could be operated by a crew of 6, a gunner, a trainer, 2 loaders, and 2 ammunition handlers. The prototype completed initial trials at the Bofors Proving Ground in Karlskoga in 1930. Swedish Navy acceptance testing followed in 1931. The gun entered Swedish service in 1936 under the designation 40mm Elvakan M36. By that point, Bofors had already begun marketing the design internationally. Poland purchased a license in 1935. Norway followed, the Netherlands, Hungary, Finland. By 1939, 14 nations had either purchased the gun outright or acquired manufacturing licenses. Britain ordered its first examples in 1937. And by the outbreak of war in September 1939, the British Army had begun establishing domestic production under license at Vickers Armstrong and other facilities. The United States was not among the early customers. The U.S. Navy had its own light anti-aircraft program, centered on the 1.1-inch quadruple mount, a weapon known informally as the Chicago piano. The Army was evaluating the 37mm automatic gun M1, a domestic design developed at WWII Arsenal in New York. The institutional presumption on both sides of the Potomac was that American engineers would produce an American solution. A Swedish gun, however effective, was a foreign design. And foreign designs carried a bureaucratic burden that domestic programs did not. That presumption would cost lives before it was finally abandoned. The 1.1-inch Chicago piano, formerly the 1.1-inch 75 caliber gun, had been in development since 1929. By 1940, it was in limited production, its specifications promising a rate of fire and hitting power that looked adequate on paper. The Navy had invested in it. Contracts had been signed. Tooling had been built. To walk away from it in favor of a Swedish design meant admitting, formally and on the record, that a decade of domestic development had produced an inferior weapon. In the spring of 1940, the Navy's Bureau of Ordnance received a formal evaluation request. Assess the Bofors 40mm against the 1.1-inch and the 20mm Oerlikon as candidates for fleet anti-aircraft armament. The evaluation team traveled to Aberdeen Proving Ground in Maryland, where a Bofors example, obtained through British channels, was set up for comparative firing trials. The results were not close. The 40mm outranged the 1.1-inch by a factor that made the comparison uncomfortable. Its rate of fire was lower than the 20mm, but its shell weight, 1.96 pounds versus the 20mm 0.27 pounds, meant that a single hit carried enough explosive force to structurally compromise an aircraft, rather than simply puncture it. The fire control system, adapted from the Swedish naval mount, allowed a trained crew to engage a crossing target at 1,500 yards, with a hit probability that the Chicago piano could not approach. The Bureau of Ordnance made its recommendation in the summer of 1940. The Navy accepted it. The 1.1-inch program was not immediately canceled. Institutional momentum kept it in production through 1943. But the decision to adopt the Bofors 40mm as the primary medium-range anti-aircraft weapon of the United States Navy had been made. Now came the harder problem. The gun existed. The design was proven. But a design on paper and a weapon on every ship in the Pacific Fleet were separated by an industrial distance that, in the summer of 1940, looked nearly impossible to close. The Navy's adoption decision in 1940 created an immediate and specific problem. Bofors AB held the design patents. The blueprints were in Swedish. The tolerances were specified in metric measurements. American factories ran on inch-based tooling. American machinists worked to inch-based specifications. And American production lines had never encountered a weapon designed to the precision standards that the Bofors mechanism demanded. The Bureau of Ordnance assigned the conversion task to the York Safe and Lock Company of York, Pennsylvania. It was not an obvious choice. York Safe had spent its entire corporate existence manufacturing bank vaults and industrial safes. Precision metalwork, certainly, but nothing that moved, nothing that fired, nothing that had to cycle 120 times per minute under combat conditions without failing. What York Safe possessed was a machine shop capable of the exacting tolerances the Bofors design required, and a management team willing to take on a contract that no established ordnance manufacturer had yet volunteered for. York Safe engineers spent the better part of 1941 converting the Swedish metric blueprints into inch-based specifications without altering a single functional dimension. Every tolerance, every cam angle, every spring rate had to be re-expressed in a measurement system that American machinists could work with, while preserving the mechanical relationships that made the gun function. It was, in the words of one Bureau of Ordnance progress report, a translation problem disguised as an engineering problem. The first American specific prototype was test-fired at the Naval Proving Ground in Dahlgren, Virginia, in late 1941. It passed. Now the question was scale. The Navy needed not dozens of these guns, but thousands. The twin-mount configuration, 2 barrels on a single-powered pedestal, required approximately 1/1700 individual components per mount. Each component had to be machined to tolerances measured in thousandths of an inch. The feed mechanism alone, the system that stripped rounds from the 4-round clips and chambered them in sequence, contained 47 moving parts, any one of which, if worn or improperly fitted, would cause the gun to jam at the moment it was most needed. The Bureau of Ordnance made a decision in early 1942 that would define the Bofors production story. Rather than concentrating manufacture in a single large ordnance facility, the contract would be distributed across multiple industrial producers, operating simultaneously. Chrysler Corporation received the primary contract for naval twin mounts. The Firestone Tire and Rubber Company received a contract for single-mount Army configurations. York Safe continued producing components. By mid-1942, subcontract agreements covered suppliers in 17 states, touching congressional districts from Michigan to Georgia to California. Chrysler's contribution deserves specific attention. The company converted a portion of its Dodge truck manufacturing plant in Detroit to Bofors production in 1942. The same engineers who had spent the 1930s designing automobile assembly sequences now applied those methods to gun mount production, breaking the 1,700 component assembly into sequential workstations, standardizing subassembly testing at each stage, and building in quality checkpoints that caught tolerance deviations before they became field failures. Chrysler's production rate reached 60 twin mounts per month by late 1943 and climbed further through 1944. The gun itself, stripped of its mount, was a study in mechanical logic. The barrel was 94.5 inches long, the bore exactly 1.75 inches in diameter. The shell it fired was the 40 by 311 mm cartridge, a brass case 301 millimeters long, propelling a 1.96-pound projectile at a muzzle velocity of 2,190 feet per second. At that velocity, the shell reached 1,500 yards, roughly the distance from which a diving aircraft began its terminal approach, in approximately 1.6 seconds. The explosive filler in each projectile was 0.15 pounds of explosive D, sufficient to detonate inside an aircraft's engine compartment or fuel system with structural consequences. The rate of fire, 120 rounds per minute, was not the highest of any weapon in the anti-aircraft inventory. The 20mm Oerlikon fired at 450 rounds per minute, but rate of fire and effectiveness are not the same number. The Oerlikon's 20mm shell weighed 0.27 pounds. It could kill an aircraft, but it required multiple hits on critical components. And at ranges beyond 1,000 yards, its projectile had shed enough velocity that those hits became less certain. The 40mm shell weighed more than 7 times as much. A single round that detonated within lethal radius of an aircraft's cockpit, engine, or fuel tank produced results that 7 Oerlikon hits might not replicate. The fire control system, fitted to the twin naval mount, translated this ballistic advantage into practical accuracy. The Mark 51 gun director, a gyroscopically stabilized computing site introduced in 1942, allowed a trained director operator to track a moving target and automatically transmit lead angle corrections to the gun mount. The director operator kept the target in his sight. The mount elevated and traversed to the computed intercept point rather than the target's current position. Against an aircraft flying at 300 miles per hour at 2,000 yards, the shelled travel time was approximately 2.1 seconds. The Mark 51 computed where the aircraft would be in 2.1 seconds and aimed the gun there. It was not a perfect system. Against a maneuvering target, the director's mechanical computer introduced a lag. Against aircraft approaching from directly ahead, the bow-on attack profile favored by some kamikaze pilots specifically because it reduced the crossing angle and made lead calculation harder. The system's accuracy degraded. Skilled gun crews learned to compensate with manual adjustment, a technique that required training and repetition. The Navy invested in that training. Gunnery schools at Dam Neck, Virginia, and at Pearl Harbor ran continuous courses through 1943 and 1944. cycling crews through towed sleeve exercises and optical tracking drills until the four-man gun crew could engage, track, and sustain fire on a crossing target without prompting from the director-operator. By the time the fleet deployed for the Central Pacific Campaign in earnest in 1944, a well-trained 40mm crew could put 40 rounds on a consistent point of aim in 20 seconds. The first American ships equipped with the twin 40mm mount in significant numbers were the Essex-class fleet carriers, beginning with USS Essex herself. Commissioned in December 1942, her original battery included 8 twin 40mm mounts, 16 barrels. By the time the class reached peak wartime configuration, individual ships carried as many as 18 twin mounts and 8 quad mounts, giving a single carrier 68 Bofors barrels capable of simultaneous fire. The Fletcher-class destroyers, the workhorses of the Pacific escort screen, carried between 3 and 5 twin mounts, depending on refit date. The Iowa-class battleships carried 20 quad mounts, 80 barrels of 40mm fire on a single hull. By the end of 1943, the Bofors 40mm had become the backbone of American naval anti-aircraft defense. It had not arrived easily. It had not arrived quickly. It had required a bureaucratic fight, an industrial conversion, and a manufacturing mobilization that touched nearly every corner of American heavy industry. But it was on the ships, and the ships were heading toward the most intense anti-aircraft environment in naval history. What happened there would prove, conclusively and at terrible cost, that the gun worked, and that nothing else in the American inventory worked as well. By January 1944, the United States Navy had taken delivery of 6,190 Bofors 40mm gun mounts in twin and quad configurations. By January 1945, that number had grown to more than 22,000 individual barrels across the fleet, a figure that represented the largest deployment of a single anti-aircraft weapon type in the history of naval warfare. Chrysler alone had produced 60,000 tons of Bofors components by the war's end. York Safe and Lock had manufactured more than 100,000 individual barrel assemblies. Firestone had delivered Army-configured single mounts to ground forces operating in every theater from North Africa to the Philippine archipelago. The gun's first sustained test came not in the Pacific, but in the Atlantic and Mediterranean, where British and Commonwealth forces had operated license-built Bofors guns since 1940. Royal Navy vessels equipped with the 40mm had demonstrated the weapon's effectiveness against German and Italian torpedo bombers during the Malta convoy operations of 1941 and 1942, among the most punishing anti-aircraft environments of the European War. HMS Victorious and HMS Indomitable both engaged during Operation Pedestal in August 1942, credited their Bofors batteries with a significant share of the 39 Axis aircraft confirmed destroyed during that convoy's passage. The data reaching Washington from British after-action reports reinforced the Bureau of Ordnance's confidence in its adoption decision. For American forces, the proving ground was the Central Pacific. The Gilbert Islands Campaign in November 1943, Operations Galvanic and the assault on Tarawa and Makin placed American carriers and escorts under sustained air attack for the first time in a major offensive operation. USS Liscombe Bay, an escort carrier, was lost to a submarine torpedo rather than air attack. But the anti-aircraft performance of the fleet during Galvanic was scrutinized carefully. Gun crews on USS Indianapolis and USS Baltimore logged engagement data that gunnery officers forwarded directly to the Bureau of Ordnance. The 40mm mounts were accounting for confirmed kills at ranges and crossing angles where the 20mm Oerlikon rounds were demonstrably falling short. The Marshall Islands Campaign in February 1944, Operation Flintlock, gave the 40mm its first large-scale engagement data against organized Japanese air attack. Fast carrier task forces operating under Vice Admiral Mark Mitcher launched strikes against Kwajalein and Eniwetok, while simultaneously defending against Japanese land-based air counterattack from Truk. During the strikes on Truk in February 1944, Task Force 58's screen of cruisers and destroyers, all now equipped with multiple twin 40mm mounts, engaged waves of Japanese G4M Betty bombers and A6M0 fighters attempting to reach the carriers. The after-action reports credited 40mm fire with the majority of confirmed aerial kills during those engagements. By mid-1944, the pattern was consistent enough to be Doctrine. Anti-aircraft defense planning for fleet operations designated the 40mm as the primary engagement weapon at ranges between 800 and 2,500 yards. The band where the aircraft was close enough for the gun to track accurately but far enough away that a destroyed or disabled attacker would not carry its debris into the ship. The 20mm Oerlikon was assigned the inner defensive band, inside 800 yards, where volume of fire mattered more than individual shell energy. The 5-inch guns with their proximity-fused shells handled the outer band, beyond 2,500 yards, where formation disruption rather than individual kills was the tactical goal. This layered doctrine was tested and partially vindicated at significant cost. During the Philippine Sea Campaign in June 1944, the Battle of the Philippine Sea, known to American aviators as the Great Marianas Turkey Shoot, destroyed Japanese carrier aviation as an offensive force. But the ships of Task Force 58 still faced coordinated air attacks on June 19th and 20th. During those engagements, 40mm batteries on the carriers and their screens were credited with the majority of aircraft destroyed within the inner and middle defensive bands. Not a single American carrier was sunk. The gun's contribution to that outcome was recorded and cited in the Pacific Fleet's subsequent anti-aircraft doctrine revisions. The Leyte Gulf Campaign in October 1944 introduced a new variable that the doctrine had not anticipated at scale. Japanese forces, recognizing that conventional air attack against a fully alerted American fleet was producing unsustainable losses for minimal results, had formalized the Toko, the Special Attack Corps, the Kamikazes. A pilot who intended to die in his aircraft changed the tactical calculus in ways that the existing anti-aircraft framework had not been designed to address. A conventional attacker, once hit and damaged, would typically break off. A kamikaze would not. The 20mm Oerlikon could put holes in an aircraft. The 40mm could destroy one, could detonate its engine, collapse its wing structure, or ignite its fuel load at a range where the resulting fireball did not reach the ship's deck. That difference, which had seemed marginal against conventional attackers, became decisive against pilots who flew until the aircraft ceased to function. During the Leyte Gulf engagements in October 1944, the escort carriers of Taffy 3, USS Fanshawe Bay, USS St. Lo, USS White Plains, USS Kalinin Bay, USS Kitkun Bay, and USS Gambier Bay, faced simultaneous attack from Japanese surface forces and kamikaze aircraft. USS St. Lo was struck and sunk by a kamikaze on October 25th, the first ship lost to a deliberate suicide attack. The 40mm batteries on the surviving Taffy 3 vessels were credited with destroying multiple attacking aircraft before impact. USS Kitkun Bay's gun crews engaged and destroyed 3 kamikaze aircraft in a single engagement window of less than 4 minutes. The data was accumulating. The conclusion it pointed toward was not comfortable. The kamikaze was a weapon that American anti-aircraft doctrine had not planned for. And the only gun in the inventory capable of reliably destroying one before it reached its target was the 40mm Bofors. Okinawa made that conclusion impossible to ignore. Operation Iceberg began on April 1, 1945. The Allied invasion force assembled for Okinawa was the largest naval armada in Pacific War history, 1,300 ships carrying 182,000 troops. It was also the largest concentration of targets the Japanese Special Attack Corps had ever been offered. The Japanese response, Operation Kikusui, Floating Chrysanthemums, was organized into 10 mass raids between April the 6th and June 22nd. In total, 1,465 kamikaze aircraft were dispatched. They sank 36 ships and damaged 368 others. They killed 4,907 American sailors. And they were stopped. When they were stopped, primarily by the Bofors 40mm. The destroyer picket line bore the worst of it. Destroyers and destroyer escorts stationed on radar picket duty north of Okinawa were the first ships the Kamikazes encountered after crossing the East China Sea. They were small ships, with limited gun batteries, positioned specifically to give the fleet warning time. They paid for that warning in full. USS Laffey, DD-724, a Sumner-class destroyer, was attacked by 22 aircraft on April 16, 1945, in a sustained engagement lasting 80 minutes. She was hit by 6 kamikazes and 4 conventional bombs. She did not sink. Her surviving 40mm crews continued firing through the entire engagement, credited by damage control reports with destroying or deflecting at least 9 attacking aircraft. Laffey's gunnery officer later reported that the 40mm mounts continued cycling and firing through structural damage that had disabled every other weapon system on the ship. USS Aaron Ward, DM-34, a destroyer mine layer, was struck by 6 kamikazes on May 3, 1945, and survived. USS Hugh W. Hadley, DD-774, was attacked by an estimated 156 aircraft on May 11th, engaged for 95 continuous minutes, and was credited by post-action analysis with destroying 23 aircraft, the majority by 40mm fire. Hadley survived, barely. Her hull was open to the sea in 3 places when the attack finally ended. The Bureau of Ordnance post-war assessment, completed in November 1945, analyzed gun camera records and engagement logs from the Okinawa campaign, with specific attention to weapon type effectiveness. The findings were distributed internally within the Navy Department and later partially declassified. The assessment credited the 40mm Bofors with approximately 32% of all confirmed anti-aircraft kills across the Pacific Theater. The highest share of any single weapon system, the 5-inch gun, with its proximity-fused shells and longer range, accounted for roughly 28%. The 20mm Oerlikon accounted for approximately 24%. The remaining figures were distributed among T-50 caliber, 3-inch, and other systems. Against kamikaze aircraft specifically, aircraft pressing attacks through damage rather than breaking off. The 40mm share of confirmed kills was assessed as higher still. The Bureau's language was measured, as government assessments tend to be. The conclusion it reached was not. No other weapon in the American anti-aircraft inventory produced comparable results against the suicide attack profile. By June 1945, total American production of the Bofors 40mm in all configurations had reached 124,135 gun barrels. Allied nations operating American-supplied or license-built guns brought the total number of Bofors barrels in Allied service to more than 350,000. Across the U.S. Navy, the U.S. Army, the British Commonwealth, the Free French, and a dozen other Allied forces. It was, by any measure, the most widely deployed anti-aircraft weapon of the Second World War. And in the summer of 1945, as the last Kikusui raids spent themselves against the picket line off Okinawa, it was also a weapon whose moment had already begun to pass. The atomic bombs fell on Hiroshima and Nagasaki in August 1945. Japan surrendered on September 2nd. The war that had driven American industrial output to levels no peacetime economy could sustain was over. And the weapons that war had validated were suddenly being measured against a future that looked nothing like the past 5 years. The jet age arrived, not as a gradual transition, but as a hard discontinuity. German engineers captured at the end of the European War had been developing jet-powered aircraft since the early 1940s. The Messerschmitt Me-262, operational in limited numbers by mid-1944, had demonstrated that propeller-driven aircraft were already approaching the ceiling of their performance envelope. The first generation of American jet fighters, the Lockheed P-80 Shooting Star, the Republic F-84 Thunderjet, entered service in 1945 and 1946 with speed characteristics that immediately exposed the limits of every anti-aircraft weapon designed around propeller-era aircraft performance. The Bofors 40mm L-60 had been engineered to engage targets moving at 200 to 350 miles per hour. The P-80 flew at 594 miles per hour at sea level. Soviet jet aircraft entering service in the late 1940s would exceed that figure. An aircraft traveling at 600 miles per hour covered the terminal approach distance, the last 2,000 yards before ship impact, in approximately 6.8 seconds. The Bofors Mark 51 Director required a trained crew and a crossing angle of sufficient width to compute an accurate lead solution. At 600 miles per hour, the geometry collapsed. The window for engagement shrank below what the mechanical computing system could reliably process. The Navy's Bureau of Ordnance recognized the problem before the war had fully ended. An internal assessment circulated in the spring of 1945, before the Okinawa campaign had concluded, noted that the L-60's performance against hypothetical jet-powered attackers would be marginal at best. The assessment recommended development of a higher-velocity, faster-cycling successor. Bofors AB, presented with this feedback through British liaison channels, had already begun engineering studies on what would become the 40mm L-70. A longer barrel, higher muzzle velocity, and an improved feed mechanism capable of sustaining a higher cyclic rate. The L-70 would not complete development until 1947. In the interim, the American Navy faced a post-war reality defined by two competing pressures: demobilization and budget contraction on one side, and the emerging Soviet threat on the other. The fleet, that had numbered more than 6,700 vessels at its wartime peak, was reduced to fewer than 1,000 active ships by 1948. Weapon systems were evaluated not for their wartime performance, but for their relevance to the next war. A war that, by 1947, American planners were increasingly describing in terms of nuclear exchange rather than conventional naval engagement. In that framework, the 40mm Bofors lost its argument before it could make one. The primary aerial threat to American naval forces was reframed as Soviet jet bombers delivering nuclear weapons. Aircraft that would approach at altitudes and speeds the L-60 could not engage. The Navy's anti-aircraft investment shifted toward the 3-inch 50 caliber gun, which could fire a heavier shell with proximity fuse to greater altitude, and toward early surface-to-air missile programs. The Bumblebee project that would eventually produce the Talos and Terrier missiles. The 40mm was not canceled by a single decision. It was reclassified, quietly reassigned from primary anti-aircraft weapon to secondary close-in battery, then to tertiary, then to reserve inventory. The 1.1-inch Chicago piano, the weapon the Bofors had replaced, had been formally declared obsolete in 1945. The 40mm avoided that specific indignity. The Navy retained it in secondary roles through the Korean War, where American ships, operating off the Korean coast, occasionally engaged North Korean shore installations and low-flying aircraft. USS Helena, CL-50, and USS Toledo, CA-133, both used their remaining 40mm batteries during shore bombardment missions in 1950 and 1951. The gun's anti-aircraft role in Korea was limited. North Korean air power was not a significant threat to American naval forces, and the engagements that did occur were handled primarily by combat air patrol rather than shipboard guns. By 1956, The Navy had removed the 40mm from its standard fit list for new construction. The last major American warships commissioned with Bofors 40mm as primary anti-aircraft armament were the later Fletcher-class destroyers, completing their final refits in the early 1950s. New construction: the Forrest Sherman-class destroyers, the Albany-class cruiser conversions, carried the 3-inch 50 in twin mounts and later missile systems where the gun batteries had once stood. The Army's experience followed a parallel trajectory. The M1 and M2 Bofors guns, the single-barrel configurations produced by Firestone and other contractors, had served in every ground theater of the Second World War. They had defended airfields in North Africa, bridgeheads in Normandy, and forward supply depots in the Philippines. The Army's post-war evaluation credited them with a confirmed kill rate against conventional aircraft that exceeded every other light anti-aircraft weapon in the ground forces inventory. The evaluation did not change the outcome. The Army, like the Navy, was reorganizing its air defense around missiles. The Nike Ajax program, entering development in 1945 and operational testing by 1951, promised intercept capability at altitudes and ranges no gun could approach. The 40mm M1 was declared excess to Army requirements in 1953. Surviving guns were transferred to reserve units, offered to Allied nations under the Military Assistance Program, or placed in storage at depots in Georgia and California. The transfer program was extensive. South Korea received 300 single-barrel units. Taiwan received 250. Greece, Turkey, Denmark, and Norway, all newly integrated into NATO, received additional allocations. The gun was leaving American service through the side door, distributed to allies who needed an ace in affordable, proven light anti-aircraft capability and could not yet afford missiles. The institutional abandonment accelerated through the late 1950s. Reserve units that had trained on the 40mm found their allocations reduced, then eliminated. ROTC programs that had used the gun for anti-aircraft gunnery instruction retired it from the training curriculum. The last active American military use of the Bofors 40mm L-60 in its original naval configuration was recorded in 1959, aboard USS Tidewater, a destroyer tender operating in the Atlantic Fleet. The mount was removed during that year's refit. No ceremony marked the occasion. No official statement was issued. The last American Bofors 40mm naval mount came off its pedestal on a Tuesday morning in a Norfolk dry dock. A crane lifted it clear. A work crew unbolted the training ring. The deck plate was welded over. The Bureau of Ordnance filed no final assessment. No program closure document exists in the public record. The weapon that had fired more than 90 million rounds in American service simply stopped appearing on the inventory lists. The Navy moved on. The Army moved on. The gun that had stopped the Kamikazes was no longer anyone's problem. Except it wasn't finished. Bofors AB did not accept the American verdict. While the United States Navy was quietly removing the L-60 from its inventory lists, the Swedish engineers in Karlskoga were already testing its successor. The 40mm L-70, the weapon the Bureau of Ordnance had requested in 1945 and then declined to wait for, completed its development trials in 1947 and entered production in 1948. The L-70 fired the same 40mm projectile as its predecessor, but from a barrel 70 calibers long rather than 60, at a muzzle velocity of 3,181 feet per second versus the L-60's 2,090. The cyclic rate climbed from 120 rounds per minute to 240. Against jet-era targets, the threat the L-60 had been deemed inadequate to engage. The L-70's performance restored the margin that the transition to jet propulsion had eroded. NATO adopted the L-70 as a standard light anti-aircraft weapon in 1953. West Germany, Belgium, the Netherlands, Italy and Norway all placed orders. Britain retained it. Sweden operated it in both Army and Navy configurations. By 1960, the year after the last American LM-60 naval mount had been removed in Norfolk, more than 30 nations were operating Bofors 40mm guns in one variant or another. The weapon the United States had quietly retired was simultaneously being installed on new construction warships in a dozen Allied navies. The irony sharpened further as the decade progressed. It's American naval planners who had bet on missiles as the complete solution to the anti-aircraft problem began encountering the limitations that pure missile air defense systems carried. Limitations in cost per engagement, in minimum engagement range, in the vulnerability of early radar-guided systems to electronic countermeasures. The missile could intercept a bomber at 30 miles. It could not engage a low-flying aircraft inside 1,000 yards. The gun, it turned out, had not been made obsolete by the missile. It had been reassigned to the engagement band the missile could not cover. The concept that emerged from this recognition, a rapid-firing cannon specifically designed to engage threats that had penetrated the outer missile defense layers, would eventually become the close-in weapon system doctrine. The Phalanx CIWS, entering American naval service in 1980, was a 20mm Gatling cannon capable of firing 4,500 rounds per minute against sea-skimming missiles and low-flying aircraft inside 1,500 yards. It was, in doctrinal terms, exactly the weapon the Bofors 40mm had been designed to be in 1930. A fast-tracking, high-rate-of-fire cannon positioned to kill threats that had survived the outer defensive envelope. The lineage was not direct. The technology was different, but the tactical logic was identical. And the naval architects who designed the Phalanx installation were well aware of the engagement data from Okinawa that had established why that band of the defensive envelope required a gun rather than a missile. The Bofors 40mm itself continued evolving. The Mk3 variant, introduced in the 1990s, incorporated a fully automated fire control system, a programmable airburst munition capability, and a rate of fire adjustable between 40 and 330 rounds per minute, depending on target type. The Mk3 does not require a gun crew in the traditional sense. A single operator at a remote console can engage, track, and fire. It is operational today on the warships of Sweden, Finland, Norway, the United Kingdom, Brazil, Thailand, and more than a dozen other nations. The platform that Janssen and Hallen began designing in Karlskoga in 1928 is, in its current form, among the most capable light naval guns in service anywhere in the world. The human footnote that the official histories tend to overlook belongs to Emanuel Janssen, the lead design engineer of the original L-60. Janssen continued working at Bofors AB after the war, contributing to the early development of the L-70 before retiring in the early 1950s. He lived to see his design adopted by NATO, proliferated across 4 continents, and credited by American Navy analysis as the single most effective anti-aircraft weapon of the Second World War. He gave no press interviews on the subject. He wrote no memoir. What the company archive records is that Janssen attended the 1953 NATO standardization ceremony at which the L-70 was formally adopted as an alliance weapon, sitting in the second row behind the defense ministers and the flag officers in a suit rather than a uniform, as engineers at such occasions typically do. The honest verdict on the Bofors 40mm is not complicated, though the American procurement story that surrounds it is. The gun worked. It worked in the Atlantic convoy lanes in 1942, on the carrier flight decks at Philippine Sea in 1944, and on the destroyer picket line at Okinawa in 1945. The Bureau of Ordnance Assessment was unambiguous. The 32% kill share figure, the highest of any weapon in the Pacific anti-aircraft inventory, was not a marginal advantage. It was a decisive one, achieved against the most psychologically and tactically challenging aerial threat American naval forces had ever faced. What the American procurement system nearly prevented, and then replicated at industrial scale with characteristic efficiency, and then retired before the weapon had exhausted its relevance, is a pattern that appears repeatedly in the history of military acquisition. The best solution is not always the domestic solution. The timeline for institutional acceptance is not always aligned with the timeline of operational need, and the decision to move on from a proven weapon is not always driven by the weapon's actual limitations. The Bofors 40mm deserved a cleaner ending from the American Navy than a crane in a Norfolk dry dock on an unrecorded Tuesday. History, in this case, delivered one anyway. The gun simply outlasted the verdict. If you found this history valuable, give the video a like. It's the single best signal you can send this channel. And if you want more stories about the weapons, the programs, and the decisions that shaped American military power, subscribe to Defense Archive. We'll see you in the next one. Somewhere off the coast of Norway, aboard a Royal Norwegian Navy frigate on North Sea patrol, a Bofors 40mm Mach 3 mount traverses silently through its automated search arc. Tracking, computing, waiting. The same Swedish mechanism that a gun crew on USS Hugh W. Hadley once fired for 95 unbroken minutes against 156 aircraft over the waters of Okinawa, still doing exactly what Emanuel Janssen designed it to do in 1928.